So I will post recordings on Canvas for now, for you all to see them. Okay.
Should we submit the homework through Canvas?
Yes, I prefer you submit through Canvas. And I mean, if it is having a difficulty, then you can email me, but I prefer that you post it through Canvas.
Yeah, okay. It's much easier to submit it through Canvas, so.
Yeah,
Okay.
that would be good.
Okay, perfect.
I can keep track of that. Thank you. Okay, so now today we are going to hello. Okay. So I want to talk about a little bit of, there are some definitions that are left to discuss. Then we will go to KVL that we were doing last time. So independent sources. What are independent sources? We talked about voltage source, current source, but we did not talk about what is independent source. So we saw them that this is our sources. So this is voltage source. This is current. What is independent source? The source that maintains constant voltage, current across instruments. That we have said before as well, right? So, but in normal mode of operation, independent source supply power, current, voltage, whatever it is supposed to do to the remainder of the circuit. So it's basically a supplier. However, in some special circumstances, they can be absorber too. What are those circumstances? Like when our car's battery dies, we have to charge it by maybe plugging another battery to it. So in that case, your source is actually absorbing the power instead of supplying it. So there are some special circumstances when your source may not be the supplier but the absorber. But most of the time, your independent source supplies the power to the circuit. What is dependent source? sources that generate voltage or current that is determined by some other thing. They are not supplier themselves. They actually, what we should say, borrow voltage or current from some specific point and then supply to the circuit. So if we draw them, if this is Vs, then we represent our dependent source in diamond. So where you see a diamond form and it looks like that it's a source, it's actually a dependent source. So if this is Vs and this is a current source, it is dependent on Vs, where G is a dimensionless quantity. It can be amplitude booster or something like that. So this is the thing that I wanted to discuss, because you were seeing in many circuits something like diamond, and it was explained something like this. So it's actually the dependent source. Then another thing that I think we have missed is Halligan's theorem. Not like very complicated, but it's just that we have to define. So what Halligan's theorem is, it says that what the conservation of energy says, right? So it says that power supplied in an electric network is equal to power absorbed by the network. So you cannot hear me?
We can hear, it's just sometimes quiet.
Sounds a little
quiet.
Sounds like you're far away.
It sounds like there's like an air conditioner blowing onto the microphone.
Now it's better.
There's a really big echo now.
Now, is it echoing still? Yes.
Yeah.
Just a minute. This classroom is actually not designed for to turn the mic off. Just a minute. Still echoing, right? Yeah. Okay. Now, okay,
Oh, the
let
echo
me
is pretty
try.
bad on that.
Yes, just fairly echoey. Hello. Now, can you hear me
Yes.
Yeah, now it's fine.
better?
Yeah.
Better than before?
Yes.
Okay. Can you understand me what I'm saying? Just let me know if it is not, okay?
Okay. You sound great now.
Good. Okay. So what we were doing, we were saying that Halligan's theorem is that you actually power supplied in an electric network is equal to power absorbed by the network, right? So means that everything, what you should say, follows the conservation of energy, okay? So these are the some definition that we have to do. Then we move to KVL. What is KVL? Kirchhof voltage law that we were doing before. Okay. So it says algebraic sum of voltages around any loop is 0, which means J is equals to 1 and Vj of t is equals to 0. That's the expression. Okay. Where Vj of t is voltage across jth branch in a loop containing n voltages. So what it means, we will explain it, okay? It is a voltage across jth branch in a loop containing n voltages. So if there are some voltages in a loop, it should be equals to 0. That's what we are trying to say. Another thing is that the voltage between any 2 points is defined as, let's say there are 2 points A and B. Between 2 points A and B is defined as VAB, right? So where VA, we should assume that this is like this, where VA is at higher potential and VB is at lower potential, right? And they are following. So if this is the element, and this is the point A, and this is the point B, then this potential is VAB, right? And we can write it as this one, as this thing as well. VA minus VN, where N is ground. So the potential at ground is 0. So this will be equal to VA, right? So when we are defining the potential between any 2 points, we define it like that. I will do an example so that it will make clear what we are trying to say, okay? So we are given VR1 and VR2, and we have to find VR3. So let's see what it is. We have a voltage source, resistor, voltage source, resistor, voltage source. So there are multiple voltage sources in the circuit. Okay, so in KVL, what we do is, do you remember what we have done in KCL? We tried to pick the node and then write what you should say, the equation, right? In this case, in the KVL, we try to pick the voltages and then we'll try to write the, so we were saying in KCL that the current entering or leaving the node is equals to 0, right? But in KVL, the voltages across any loop is equals to 0. So this is the difference between KVL and KCL. So in KVL, if you define how you're gonna write this circuit's voltages, I prefer to write or draw the arrow like that in a clockwise direction and then write the voltages, right? So it will make it easy to understand. So what I am doing is, okay, so what this loop suggests? This loop suggests the direction of current, right? So you can start writing from any side, but you need to think from where the loop is entering to any element, okay? So let's see if, let me define the nodes as well. So this is my A, B, C, D, E, F. We will also explain that when we should use KCL and when we should use KVL. So we should not worry about that. So another thing, why I'm drawing the loop, because this loop is suggesting which polarity I should take when I will write the equation. Okay, so what this loop is suggesting, take the polarity of from where the arrow is entering the element. Okay, So let's write it. So if I write this, I will start from 30 volts, right? So arrow is entering from which sign into the 30 volt?
From the negative side.
Yes, that's true. So it is entering from the negative side, right? Then, so minus 30 volt I have written. Then VR1, what should be the polarity? Can you see the polarity of VR1? So from where the arrow is entering in the element?
Positive side.
Positive, right? Okay. VR1. Similarly, minus 5 volts plus VR2 minus 15 volts plus VR3. So we covered all voltages in a loop. And is it right? Do you think that it's following the arrow entering into the element sign, all of them?
No, it's going the other way around, right?
What is going other way around? Arrow?
The arrow.
Arrow is going which way?
I mean, if all the voltages are negative, it's probably going in the counterclockwise, isn't it?
Okay, okay. So what I'm trying to say, you don't have to think about right now what is supplying and what is absorbing. I'm just trying to write the equation, and the equation follows the loop direction that I have drawn. Okay, so I have drawn a what you should say arrow, and I'm saying that my equation should follow the direction where arrow is entering in the element. Okay, sounds good? So I'm just writing the equation. I have to rearrange this equation, right? So this equation gives me the basis to solve the question. So right now I'm just not saying what is supplying or what is absorbing. I'm just writing the equation. Okay, so let's see. VR1, so if I rearrange this, VR2 plus VR3 will be equal to 5 volts plus 15 volts plus 30 volts, which is equal to, right, 20 and 50 volts, right? And step number 3 is, if VR1 is equal to 18 volts and VR2 is equal to 12 volts, then what is VR3? So it is, VR3 is 50 volts minus 18 volts minus 12 volts is equal to 20 volts. Okay, so you understand what I'm trying to do. And what is VR1? It's actually as we have defined the Ohm's law before, we can say VR1 is actually IR1, right? Similarly, VR2 is actually IR2, and VR3 is actually IR3. From where I comes in. So this is the arrow that I'm drawing is nothing but I, right? So this is actually I, and this same I is flowing in the circuit. If you remember in KCL, we were having, if I just draw to remind you, we were having something like this. Right? So we were saying that this is the node from where the current is entering or leaving, right? So in this case, there is no one I that is flowing in whole of the circuit. But in this case, if you see, all the elements are connected in such a way that one current is flowing in all of the circuit. There is nothing, no branch in between to divide the circuit, okay? So in such a circuit, we are just taking one I and trying to write the equation. Is it clear a little bit?
Wait, I have a question.
Yeah.
Can you explain again how you said that the VR1 is equal to the IR1?
Yeah. So what you are saying how it is equal to IR1?
Yeah.
Okay. So do you remember Ohm's law? Ohm's law was that V is equal to IR, right?
Yeah.
Right?
Yes.
So we have said that voltage is equal to IR. So, and we also said that the passive components have a voltage drop across them, and we define something like this, the passive sign convention, right? So if there is a current flowing in it, there is a dissipation of energy, and this voltage will be IR, right?
Yes.
So if this, I just by reference define that this is my R1. So this is the reference. So this is VR1. Maybe I should write a small subscript. So then this will be IR1, right?
Okay. Yeah.
Is it clear now?
Yes, thank you.
Okay. So if it is clear, then I'll move forward. Is it clear to everyone? Or anybody has question? Because, okay, because it's very important to understand the difference between KVL and KCL. But when I'm describing KVL, you should not think about KCL. You just focus on KVL, then it will become more easy to understand. Okay. So this is how I found the voltage. So these VR1, VR2, and VR3 are just the references of voltages across R1, R2, and R3. Okay. So I will write another equation to make you, comfortable, and let's think about it. Okay. So let's say if I have this network. in this network, you can see that there are multiple loops, right? Loop, what was the loop? Loop was the closed branch or closed path that has the multiple elements in it. So this is a two closed paths. We can apply, so there is a node in which the current is dividing as well. But for KVL, for describing KVL, I will try to write the equation of the loops in terms of KVL, okay? So let me define first the, what you should say, voltages. So this is 24 volts plus minus VR1 plus minus VR2. So it's R1, that's why we are defining it like that. R2, R3, R4. So this will be plus minus VR3 plus minus VR4. This is 8 volts and this is 16 volts. So when we draw the, the current path, we take one direction only. So we will do, so this is one current and this is another current. So let's say this is I1 and this is I2, right? So I will not try to solve it, but I'm just writing the equation to understand what we are trying to see, okay? Say. So let's say. Applying KVL. In first loop, I will apply KVL. Okay. So what should be the equation I should write? Can you write with me? So first loop, loop 1 where I1 is flowing. So I am starting from 24 volts. So this is minus 24 plus VR1 plus VR4 minus 16 volts is equal to 0. Okay. Now I will write equation for loop 2. Yes. So what should be the equation? Or I should write here maybe. So or no, like that. Yes, please. What should be the equation? Where should I start from and what should I write?
16.
Plus 16, yes.
Plus 16.
Yeah.
Minus VR4.
Yes.
Plus VR2.
Right.
Plus VR3. Plus
yes.
8.
Yes, that's it. Yeah. So that's how you write equation around the loop. You think about from where the arrow is entering and just write the signs. Is it clear? Okay. So we will not discuss multiple loops till we reach some difficulty, or we will not try to solve it. This is just try to give you an idea that how we should be able to write the equation in the complex formats as well. So let's try to solve another question. Consider the following network and find VAE and VEC. Okay, so let me write the network. Okay, so this is 24 volts. This is 16 volts. This is 12 volts. This is 4 volts. This is 6 volts. This is 10 volts. Okay, let me define nodes. A, B, C, D, E, F. Okay, so there are two types of voltages that we have to find. Okay, so one is we will go step by step. So one is VAE. So VAE is like this. So VAE has two parts. Like VAE, if we think about the voltage, the 2 points between which we have to find the voltage, it's involves 10 volts and 24 volts or the rest of the circuit, right? So to find VAE, what I will do, for my ease, I will draw the loop, okay? That's how the current is flowing, okay? Direction, okay? Then my step 2 is if I want to find VAE, right? I know we can write this equation, okay? Can we write the equation applying KVL? Let's write it. Like just write the whole equation, okay? It is 24 volts plus 16 volts minus 12 volts plus
Wouldn't it be
4
minus 24 volts?
Yes, it is. I just deliberately did that so I would know that you're awake. Plus 10 volts, okay? So this is the equation, right? We know everything. We know everything, but we need to know VAE. So I just wrote this equation, but we don't need to write this equation just to solve VAE, okay? Okay. So what I should do to find VAE? I will replace or consider a black box around VAE, okay? So let's see. I am drawing a black box. Okay, so there are two ways I can draw this black box. So this is VAE, and I will draw the rest of the circuit. Should I include the 10 volt in this circuit? or the resistor voltage, this one?
No,
No.
because it's part of the box.
What do you think? It should be in the box or out of the box?
In the box.
Why?
Because it's in between points, nodes A and B, or A and E in the circuit.
Yes. Yes, that's true. So it should be in the box. So we should not include it here, okay? So I just write it here like this. So now we know this black box is VAE, right? So we will just write the rest of the things. Okay? And let's write the equation. VAE minus VAE, if I just draw this,
How did you know which side of the VAE to put the plus and the minus?
that's a good question. So, okay, so I just put plus and minus according to the signs I have, okay? So, if I put plus and minus like this convention sign of plus and minus, then let's see what it will do, okay? So I just put the plus and minus like the convention sign, if you see here. I think this will be more explained when I will be doing VEC, because VEC, if you see, has minus and plus, yeah, right? V is down and C is up, right? So I just took plus and minus by convention. You can see that, say that, okay? And it will be more clear when I will do that, like when I will solve it. So minus VAE plus 16 volts minus 12 volts plus 4 volts plus 6 volts is equal to 0. So it will become VAE is equal to minus 16 volts minus 2 volts, plus 2 volts, sorry, minus 14 volts, VAE, right? Okay. Just to verify that, I can do another thing, okay? I can put the rest of the circuit in the black box and try to find the other part of the circuit, okay? Let's try to do that. And just to verify what I'm doing is right or not. This is VAE, and the rest of the circuit is also, if I think about these two nodes, it's also VAE. So I will just try to VAE. So this was my 24 volts. And this was my 10 volts. Okay? Let's write this equation again. So it's 10 volts minus 24 volts plus VAE is equal to 0, which makes it VAE Is it right?
I think the first one is wrong because you kind of just dropped the negative in front of the VAE.
Oh, yes, that's good. Okay, because there was also negative here, right? So it's positive. Yes. See, that's how we can verify what we are doing is right or wrong. So this is 14 volts. Got it? Is it clear?
Yes.
And another thing I want to explain, I think I just got the thing that you were asking. Someone was asking, how do you know where to put positive and negative sign, right? Who was that? Who was asking that?
That was me.
Okay, Aiden. So Aiden, do you remember that we have defined that VAB is VA minus VB, right? Right?
Yes.
And for that, we don't know whether VA is at higher potential or VB is at higher potential. We don't know that. But we just go by the name, okay? So we define it like this, VA minus VB. So if someone is asking, find VAB, you don't know what's in the box, but you just give the sign, okay? So you will put VA, if this is your A and this is your B, you will put this sign. Understand? Because now if I want to find VEC, what should be my signs?
E should be at the top, the positive end.
Yes, that's very good. So this should be my sign, right? So this tells me the convention. The name tells me the convention. Okay? Understand? Aiden, do you understand what
Yes,
we are
understand.
trying to say? Okay. So let's try to do VEC. That will make it more clear. Okay? VEC. Okay. So I have to put VEC in the black box. Okay. So let's see what VEC is. Okay. So this is my VEC, right? But you can see that VE is lower than C. So I don't know. Okay. I don't know what this is. I will just put them in the black box and take the convention as the name. Okay. So let's do that. So it should be this because E was down. Okay. So this is 10 volts. Minus 24 volts, 16 volts, there was another resistor, okay, minus 12 volts.
Why is there only one resistor on the bottom?
Yes, it should be another. No, yes, because now I am thinking about VEC, right?
Oh, okay, yes.
Right?
Mm.
Okay, so 24 volts and 16 volts. And I should keep the signs as well, plus minus. Okay. And this was 10 volts. Just need to confirm. Okay,
So plus minus 10 volts, 24 volts, 16 volts, 12 volts, okay? So we are good. Right? So we have to write the equation for VEC. Applying KVL, draw the loop direction, whatever arrow is like that. Okay, and then write it, the equation. Minus 24 volts plus 16 volts minus 12 volts minus VEC plus 10 volts is equal to 0. So it will become okay, VEC is equal to 16 minus 2, 14, minus 24 plus 14, and VEC is minus 10 volts, right?
Yep.
So now we are clear that how we are trying to define the voltages, okay? You should be very clear about the names. So if it is VAB, we are trying to define a sign as plus and minus, okay? Are we feeling good about that? Okay, so let's move forward. So I will just try to now define some things that we will use in future. I mean, they are coming all the time, so I just feel that we should define it. So let's try to define that. What we are trying to do. Okay, series circuit. What is series circuit? We are all the time seeing the circuits that are connected in some way or another way. So I will, we should define that, okay? So let's see that this is a circuit I have. This is V in, this is R1, R2, R3, plus, minus, plus, minus, plus, minus, okay? So these components are connected in series. Do you understand the series concept? Like the series means that they are connected to each other in series. And the parallel means that they are connected to each other in parallel, like they are going in parallel to each other, okay? So another thing of thinking about that is components connected in series contain same current flowing through them. So that's what we have defined before as well. So if this is the component, this is the series circuit, or these are the components that are connected in series, they have only one current flowing through them, okay? So let's define their equation using KVL. And normally in series circuits, we use KVL. That's why we use KVL around them. You will understand that why KVL is easy to use in series circuit, right? Because we are concerned with the voltages because the current is same. So let's write the equation. okay? Minus V in plus VR1 plus VR2 plus VR3 is equal to 0, okay? Minus V in plus IR1 plus IR2 plus IR3 is equals to 0, because we know that Ohm's law says that V is equals to IR. I just write it as it is. VR1, VR2, and VR3. Okay. Now, minus V in plus IR1 plus IR. I can do that as well. Okay. And let's say that, okay, minus V in plus IR, S is equals to 0. So V in is equal to IRS. Where, what is RS? RS is R1 plus R2 plus R3. So this is how S means series, okay? So this is how series resistance can be found out. Okay? So we understand that this circuit, in this circuit, components are connected in series. That's why we have series resistance. Okay? Now we think about the circuits that are connected in parallel. Okay? So it will make it easy for us to understand or deal with the circuits in future. Parallel circuits. So the parallel circuits, as opposite to the series, the components are connected in the parallel form. For ease, I'm just drawing the current source, okay? It doesn't mean that you cannot draw the voltage source here. There can be n number of resistors, and similarly, there can be n number of resistors in series too, okay? So if this is my I naught of t, this is my okay, R1, R2, Rn, I1 of t, I2 of t, In of t. So the direction of the currents are opposite to I naught of t. Okay. So now if I apply KCL, I can apply KVL too in this circuit, but KCL is easy because I can see that currents are dividing in the circuit. That's why it will be easy to apply KCL. So I should write components connecting in parallel contain same voltage across them. So there is one node here that has the same voltage, right? So that's why it's easy to apply KVL. Oh, sorry, KCL. Okay, so applying KCL, I will write the equation. Okay, so my equation will be as I'm thinking about only the node, so my equation will be minus I naught of t plus I1 of t plus I2 of t plus In of t. So if there are n number of things, I should be doing this, okay? So then I naught of t, I1 of t plus I2 of t plus In of t, where my I1 of t is V by R1, I2 of t is V by R2, In of t is V by Rn, right? So if I just replace it here as I naught of t, which is the source, and replace all these here, it will become V is common, we can take it out, 1 of R1, 1 of R2, 1 of Rn. From where I get this, because we know that V is equals to IR, I will be equal to V by R. Okay, so this will be equal to V by Rp, I naught of t, and where Rp is one over R1 plus 1 over R2, 1 over Rn. Can I also write it like this? Right? So that's how we find parallel resistance. So if you see that this is a parallel resistance, and that was the series resistance. Okay? Are we clear about that?
Yeah.
Okay. So when it will come in future, we will understand that if the components are connected in series, how to find our resistance. If they are connected in parallel, how to find our resistance. I mean, it's not like that it's will not be complicated at all, but we will at least understand that how to proceed. Okay, so another interesting phenomena here is, I mean, you will do in ENG 214 as well, that if you connect the resistances in parallel, the equivalent resistors or the RP will be lesser than the smallest resistance you have in the network. I mean, you will learn that in ENG 214 as well. So it's okay. So now we are doing, so RP is the parallel resistance. Another thing that we all the time talk about is voltage division. We are doing the voltage division. Okay. Okay, so let's do this circuit. So voltage division, as the name says, that we will divide the voltage. We will divide the voltage means, like, if we have input voltage, we can control the output voltage by putting resistors or the components in the circuit, and we can control our output, right? So I think some of you have done with me in the lab too, but we have not defined the theory yet. So what is voltage division? So this is VR1, this is VR2, this is VR2, and this is V of t, or V, what you're saying, okay? So I am saying, I mean, this is the ideal scenario when we are trying to measure VR2, and we will think that there is no open circuit, that is RL is infinity, ideally IL is 0, and this is the ideal scenario. Okay, so we are just trying to measure VR2. So applying KVL here, I will do this. Minus V of t plus VR1 plus VR2 is equals to 0. V of t is equals to VR1 plus VR2, right? According to Ohm's law, we know that VR1 is equals to R1 I of t, VR2 is equals to R2 I of t. And if I replace this as it is here, I will write it as R1 I of t plus R2 I of t. And then it will become right? R1 plus R2. Now I know the current. Now, if I plug this in, if I try to find VR2, let's try to find that. Okay, so VR2 is equal to this, right? R2 I of t. So if I plug I of t here, so VR2 will become, so what we have defined here is that how we will find that what is VR2, how much is the VR2 that we are getting, or how we will design that if I have 10 volts of input, how much output voltage I'm getting. So this is how that VR2 is quantitatively defined, that how we will be doing it, right? So this is VR2, and VR1 will be R1 I of t, right? So VR1 will be R1 V of t over R1 plus R2. VR1 will be R1 over R1 plus R2 V of t. So this is, if you want to find VR1, you can find it like that. Okay. Another interesting thing is that if you know about transfer function, have you heard about them in some class or something? Okay, so the transfer functions are when you define output by input, right? So here, if you say that your VR2 is your output voltage, right? So you can define V out by V of t is equal to R2 by R1 plus R2. So this will be your transfer function for voltage divider. Okay, so it's not very complicated thing, but I mean, some people define it in that. What are the transfer functions? There are some complicated one, but I want just to think about transfer function like that. Okay. So another thing is that you saw that voltage divider is actually used to divide the voltage or control the output voltage, right? But what are the advantages of the voltage divider? Let's see. Voltage divider is easy to design, build, and implement. I mean, you can select some resistors and you can select your output voltage. Okay. What is the disadvantage? Voltage is dividing, or you are controlling division by voltage drop, right? So voltage division happens at the cost of energy dissipation. How? I mean, you are getting some output here, right? But for that, you have some voltage drop here because you have to down the voltage. So this here, you are actually dissipating the energy, which is causing the voltage drop. So heat is dissipated across R1, right? So I will just quickly try to give you an example of voltage division like we have done in the, I think, like the lab 2, that we have, let's say we have selected R1 as 1 kilo ohms and R2 as 1 kilo ohms. Then our V out was R2 by R1 plus R2 into V in, right? So R2 was 1 plus 1, and V in was, let's say, 9 volts. So it was 1 by 2 into 9 volts, and it was 4.5 volts, right? Do you remember doing that?
Yeah.
Right. So that's we designed voltage divider to half the voltage at the output. But we can also design it to in a different way. Let's say we have R1 as 1 kilo ohms and R2 as 2 kilo ohms, right? Then our V out will be 2 divided by 2 plus 1 into 9, 2 by 3 into 9 volts. And V out is 6 volts, right? So by controlling either of the resistance, like R1 or R2, you can change your output voltage, or you can control your output voltage. We will continue voltage divider from, like, I want to talk one small thing about that, but I think we are out of time today. So I will stop here. Thank you for joining me. And if you do not understand anything, you can stop me in the lecture, or you can email me, or you can ask next time. But we should be very clear about what we are studying. Okay, thank you.
Okay, bye.
Thank you.
Thank you, bye.
Thank you. Have a good day.
Sam.
Bye.